Howdy, howdy, this is Mr. Potter. In our last video, we talked about the worst phone book in the world. A phone book where everything was in order by telephone number, and if I wanted to find my friend's number, I would have to look at each telephone number starting at the beginning and see, is that my friend's number? And I either got a yes or a no. We talked about that being a linear search. But that's not the way that most telephone books are. We do have better telephone books. I can imagine that I have a telephone book, and when I look at this telephone book, the first thing I see are names that start with A. And in here, I'm going to find all the names that start with A. And then maybe a few pages in, I'll find all the names that start with B. And they're going to be in this alphabetical order, something we call lexicographical order, the order of the alphabet, or the order of our lexicon. And each one of these names has a telephone number that goes with it. Well, if I know that my friend's name starts with an R, there's no reason for me to start looking at the A's and the B's. What I can do is I can kind of flip to the middle of this, and I'm looking at the middle, and of course, if I look at the middle here, these are going to be all A through M's, and this part's going to be the N through Z's. I'm like, okay, my friend's got to be on this side. I really don't need this half of the phone book. And if I was a strong man, I'd just rip that part off, throw it away, and say, okay, now I want to look at N through Z. I'm going to cut it in half. And so I'm going to look at that half of the phone book, and I'm going to say, okay, N through T and U through Z, and I don't need this half of the phone book. So I could rip that part off and only look at this. And the idea is that we're really using a divide and conquer technique. The idea that I can take the entire alphabet, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. And I can say, okay, I'm going to cut this alphabet in half, and because I'm looking for the letter R, we're going to get rid of all of these. So in other words, after one pass, I've eliminated the front half of the alphabet. And now I'm going to cut this in half, and after my second pass, I'm going to get rid of this half of the alphabet. So after two passes, I'm down to the quarter of the alphabet that I really want. And then I'm going to cut this in half and get rid of the half that I don't need. That's after my third pass. So now I'm dealing with 1/8 of the alphabet. And then I'm going to cut that in half, get rid of the half I don't need. This really is 1/16 of the alphabet. Now, of course, I'm saying 1/16 in air quotes because really this is just some fraction of the alphabet that's getting smaller and smaller. When I make this final division, that's my fourth division. Actually, that's my fifth division. This is my fifth division. Now I'm looking just at the R's. And now I can say, okay, is his name R-A, or is it R-E, or is it R-O, or is it R-I? Maybe it's an R-H in there. But I can take a look at that and do the second letter of the alphabet in that same way. So the idea about this dividing and conquering is that the first thing that I'm going to do is I'm going to break the list in half. And then the second thing I'm going to do is only look in the good half. Because if I know my friend's name starts with R, there's no reason for me to look at A through M, because my friend's name will not be there. And what I'm going to do is I'm going to continue this over and over and over again. Keep dividing in half, only look in the good half. Divide in half, only look in the good half. And this idea of dividing and conquering is going to help me find this, and as we'll show in a bit, it's actually going to help me find it much more quickly than our linear search technique would. So let's jump to this. The big but here is that these things have to be in order. I couldn't have an alphabet like A, K, M, O, T, B, Z, F, N, H, R, T, Y, P, L, and the rest of the alphabet, because then if I cut my alphabet in half, I'd have to know what the order is, because I'm really comparing myself to these letters here. And it's just a coincidence that R happens to be there. So if I really cut, let me undo some work here. This is about halfway through here. So the question is, do I belong in the half with the Z or do I belong in the half with the F? Am I less than Z or am I bigger than F? Well, both. And that's a problem. So the big but here is that this only works with ordered data. Ordered data. In other words, it's only going to be able to work if I can put this data in a particular order so that I can say, okay, I belong in the first half of this set of data, or I belong in the second half of this set of data. If I don't have the data ordered, then I'm going to run into problems. So, we have to assume that our data is ordered. So we're going to assume ordered data. And I'm going to put a star by that because what we're going to have to do after this is talk about, okay, how do we sort our data? But that's a video for another time. Today, we're talking about the idea of a binary search. And here is our pseudocode. Now, this is a little bit longer because this technique is a little bit more involved, this divide and conquer technique. However, to make up for the complicatedness of it, we're going to find that this is much more efficient. I mean, astronomically more efficient. That's really what we're going to get to with today's lesson. So, as we did before, we're going to allow the user to type in some number, and we're going to store it in a variable called target. But keep in mind that when I have a list, I'm going to have to keep track of the low end, I'm going to have to keep track of the high end, and I'm going to have to find the middle by taking the average. 0 plus 32 is 32, half of that is 16, and this average is always going to be exactly halfway between the low end and the high end. And I'm going to assume that I haven't found it because I haven't started looking for it. And I'm going to repeat this process until one of two things happen. Until either I find what I'm looking for or this right here. And this seems weird, but I want to keep going until the low end is higher than the high end. Because you may recall that was kind of the situation we had here, where if I've got this situation where both of these things happen to be true, then I'm going to run into a problem. And we're going to talk about how to address that problem in just a moment. So, if the thing that I'm looking for is spot on, I found it, I smack dab, I cut the list in half, and you know what, it's in box 16, that's great. I found it, and I'm going to display it. If it's not, then I have to ask myself, okay, is what I'm looking at bigger than what I'm looking for? In other words, if what I'm looking at is bigger than what I'm looking for, I'm too big, and I need to eliminate that top half. And so what I do is I say, you know what, it's not in box 16, it's not past box 16, I don't really need to look at anything beyond box 16, so I'm going to say the highest I'm going to look for is that 16 minus 1. In other words, box 15 is the highest I ever need to look ever again. And of course, the opposite is true. If what I'm looking at is smaller than what I'm looking for, then I know it's not in the front half of the list. I know it's not in box 16. I know it's not in any of the boxes before 16. And so box 17, this box that's one more than what I'm looking at, is the smallest that I'd ever have to look at. And then I need to recalculate. I'm going to take 0 plus 15, add them together, divide by 2, and look at box 7. Now keep in mind, I really need to consider this being integers because there wouldn't really be a box 7.5. So we're only going to be dealing with integers. But this idea allows me to do the divide and conquer. And I'm going to repeat until this situation happens. And we're going to talk more about this in our second example. But this is going to be the situation where if I keep dividing and conquering and say, nope, it's not here. So we're going to look at box 8. And then that gives us a 12 that we're looking at. And no, it's not here. So I'm looking at box 11. And no, it's not here. Eventually, these numbers are going to cross each other. And if they ever cross each other, that means that my data is nowhere to be found in the list. So we're going to do two examples with this, just as before, just as we did in our last video. We're going to be searching for the number 12. So I'm looking for the number 12, and I'm telling the user, hey, look for 12. So 12 gets stored in target. Low is going to get 0. And in this case, I've got 0, 1, 2, 3, 4, 5, 6, 7, 8. So the length is 9. So I'm going to put a 9 in high, and spot is going to be 0 plus 9, which is 9, divided by 2. And I said we were going to deal with integers, so I'm looking at box 4. This is the box that I'm starting at. And I'm going to repeat until it's found or until we cross the streams. Is what I'm looking at in box 4, is that a 12? And the answer is no, that's not a 12. So is what I'm looking at in box 4, is box 4 bigger than a 12? And yeah, it is bigger, which means it's not in box 4, and it's not going to be anywhere else past box 4 to the right. Well, if I get rid of all of this data, that means the biggest thing that I have would be 4 minus 1, which is 3. And that means that high is now a 3. Now I know spot is supposed to be low plus high divided by 2, so I've got 0 plus 3, which is 3, and 3 divided by 2 is 1. So now I'm looking at box 1. Okay, so looking at box 1, here's box 1. Is that a 12? Well, no, it's not a 12. Okay, is box 1, what's in box 1, bigger than 12? No, it's not bigger. 8 is not bigger than 12. Is what's in box 1 less than 12? And the answer is yes. So that means my low end is going to move up. It's not in box 1, and it's not anywhere before box 1 in our list, which means this is now our new low end. So in our low end, low is now 2. 2 plus 3 is 5. Half of 5 would be 2.5, so let's just call that 2, and we're going to look in box 2. So is box 2 a 12? Well, yeah, it is. And so that means found is true. And so if found is true, we're going to jump down to here and say if we found it, then our display box 2. Box 2 is the spot that the 12 ended up being in. So let's talk about what happens when 12 doesn't show up in the data. So here's our bad situation. We're talking about 12. There's still box 0 is our low end, box 9 is our high end. 0 plus 9 is 4.5, so that's still box 4. I'm going to start looking here. So is it in box 4? Is box 4 a 12? No. This is the situation where it's too high. And so the high spot is now going to be 3. So now I'm searching between 0 and 3. This is exactly the same as it was before. So now, once I know that high is 3, I'm going to be doing it 0 plus 3, which is 3, divided by 2 is 1. And so now I'm going to be looking at box 1. So is box 1 a 12? Well, no, it's not a 12. And this is the situation where what's in box 1 is less than my target. So low is going to be spot plus 1, which means low is now 2. It's nowhere on this side of my graph. And when I look at this, I'm looking at this and saying, okay, if I take 2 plus 3, that's going to be 5. 5 divided by 2 is 2. So now I'm looking in box 2. Is box 2 a 12? Well, no, that's a little too big. So what's in box 2 is bigger than 12. High is going to be spot minus 1, so high is not 3 anymore. And it's not 2, high is 1. So let's see, low is 2 and high is 1. And this is that situation where my low is bigger than my high, and I've been able to eliminate every number in my list. This is a problem. If I ever reach this situation where my low number ends up being bigger than my high number, then I know my data can't be anywhere in the list, and I'm going to fall out of the loop. Found stayed false. We never reached this one line of code, this one spot that would allow us to change found to true. So we have to drop to this else statement. This part's not true, this part is true, and we say that it's not found. So when I'm looking for data using a binary search, I'm going to be using this divide and conquer technique. The idea is that every time I do a pass, I get rid of half the data. So just like we did before, we do have a best case and we do have a worst case. And just as we did with before, our best case is it's going to be in the first spot we look. In other words, the first time we look, it's going to be in the middle. It takes one search, one pass to do it. For our worst case scenario, it's actually a little bit more interesting. Let's say that I had 1,000 elements in my set. Well, the first time that I look, I'm either going to find it or I'm only going to make sure that there are 500 spots that aren't there. The next time when I cut that in half, it's going to be 250. The next time I cut that in half, it's going to be 125. The next time I cut that in half, because it's got to be an integer, there are only 62 boxes to look at. The next time, there's going to be 31 boxes. The next time, because it's got to be an integer, half of that is 15. The next time, it's got to be half of 15, which is 7. The next time, half of that is 3. The next time, half of that is 1. And it's either there or it's not, so it's going to take me 10 passes to look at 1,000 numbers. Which means my worst case scenario, if I had 1,000 pieces of data, is 10. And what I actually find out, it ends up actually being a logarithmic growth. In other words, if I actually start off with 1,000,000 pieces of data, it would take 20 steps for me to say, yes it is and here it is, or no it's not. Well, that's wonderfully efficient. Much more efficient than in the case of the linear search, where I'd have to look through all 1,000,000 telephone numbers in my telephone book. Here, I only have to look at 20 pages of my telephone book and I can immediately tell you, yes, he's on this page, or no, he's not. And that's the power of the binary search. Yes, it is a little bit more complicated in the coding of it, but my goodness, the benefit that we get is so much more advantageous. So, once again, this is Mr. Potter. Thank you for watching. Have a great day.